Well, thank you all for being here today. I'm really happy to be here speaking with you about cloud, about innovation. I wanted to start by talking a little bit about Amazon and how Amazon got into this space, why we care so deeply about semiconductor design. I'm going to talk also about IoT and connected devices, what's really driving next generation innovation in semiconductors, some of the products that are of interest out there, and how AI and machine learning fit in. But then I'll focus very quickly on EDA because it's super important to us. It's obviously critical to the audience here today. First, when we think about Amazon over the years, Amazon has grown obviously. We're in many different businesses, and a great way to think about Amazon today is as a global logistics and operations company, right? Whether it's delivering products, whether it's operating fulfillment centers, whether it's what we do in consumer products, we're all the way up and down the stack. Everything from logistics and operations of a cargo airline down to designing silicon chips for our own networking infrastructure and for our consumer devices. So we are users of EDA tools, increasingly significant users of those tools. We do a lot of chip development at Amazon. We're in the ecosystem in a big way. And of course, we enable customers through AWS to do the same. Many of the learnings that we have internally in our own semiconductor teams have helped us to help customers externally to use AWS services for EDA and other related high-performance computing workloads. And I'll talk about some of those best practices in a few moments. But I thought it was very important to set the stage with why we care so deeply about semiconductor design and about EDA at Amazon. It's very, very important to us. Now here's an eye chart, also helping to explain why this is so important to us. If you think about cloud applications today, many cloud applications operate on data that's coming from outside the cloud, edge devices, right? So this may be industrial automation use cases, it may be connected consumer products, it may be voice recognition in services like our own Alexa-based products, right? Echo, Spot, and Dot, and so forth. Maybe it's image processing coming from sensors. It's infotainment in automobiles. There are so many emerging use cases for connected devices, and these use cases require cloud, of course. Not only for back-end analytics and machine learning, but also for device management, for managing thousands or potentially even millions of sensors and intelligent devices at the edge. So design of these devices, the embedded systems and the silicon devices themselves, is a very important part of next generation product development. And again, we're very serious about this, whether it's EDA, whether it's development of embedded systems, offerings like the Greengrass and FreeRTOS services that we have for edge devices. IoT plus cloud is a very, very important area for us, and it's closely associated with design and verification of next generation semiconductor devices. So to summarize that, we operate in the cloud. Obviously we have cloud resources now in a large number of global regions with an even larger number of availability zones that allow customers to scale quite dramatically their engineering workloads, their core IT workloads, machine learning and analytics workloads, and we operate at the edge by offering services that can operate within embedded systems. FreeRTOS, for example, with Amazon APIs and SDKs to communicate securely with the cloud. Greengrass, which is a set of SDKs that run in an embedded device running Linux, right? These allow you to securely communicate from the cloud to the edge device. Let's talk now about machine learning, because machine learning is very, very important to Amazon, and it has been for a long time. I've listed just a few of the use cases at Amazon that have existed for years. And many of these use cases now are being exposed as services that are available to our own customers who develop new applications on AWS. So let's say, for example, that you're creating a next generation system on chip that's going to go into a industrial automation product with an embedded system communicating securely to the cloud. You need higher level services on the back end, whether it's image recognition, large scale analytics. Do you want to detect transactions, for example, that may be fraudulent? So many use cases now require these higher level services, and they require the massive scale of cloud to do machine learning training and inference, collection of data, and actionable insights on that data. I mentioned scale a moment ago, and this is a theme I'll return to when I talk about EDA. If you're doing machine learning today, you need massive scale. You need perhaps petabytes of data to train on, whether it's image data, whether it's log data, whether it's natural language processing types of data. Training of machine learning models requires vast amounts of scale in storage, but also in compute. Increasingly, deep learning training takes advantage of GPUs. And so the availability of large fleets of GPUs running for relatively short periods of time to do that deep learning training is a very big enabler. It's very important to next generation AI. It really does require the scale of cloud to effectively take advantage of machine learning, deep learning technologies, right? The inference that you generate from deep learning training could be deployed in the cloud, or it could be deployed in those edge devices. So let's say I'm training a model on some images using MXNet in the cloud. I want to push that inference out to the edge device. So again, this is where Amazon Web Services has capabilities both in the cloud for that training and inference, but also to push the inference down into the embedded device that may or may not be connected to the cloud all the time. So the theme here, what I really want to get across is that cloud is no longer just services and storage and compute in a contained environment of cloud. Cloud now extends to the edge. It's very important for next generation applications that are based on intelligent connected devices. If we think about machine learning applications in semiconductor, there are many, right? Some of these are aspirational, some of them are very real today and already in deployment. On the EDA side, you can think about machine learning for some very pedestrian types of applications, like analyzing the job logs that come out of your LSF cluster, getting some insights around that, perhaps to predict utilization or predict resource requirements for the next run of regressions. Perhaps you're looking for usage patterns among your users to optimize license usage, for example. Machine learning could certainly play a role there. And in the EDA tools themselves, there's many opportunities today and in the future for machine learning to help. Intelligent routing, for example, or DRC. Perhaps more interestingly is on the back end, on the manufacturing side. So if you're a foundry, if you're an equipment provider, you'd really like to know how to improve yield, right? And some of this information may be very proprietary within the foundry, very proprietary within the machinery in the foundry. Some of this data might want to come back out to better inform simulation and verification at the front end for design for manufacturing. It's a very important trend now in the use of machine learning and IoT for industrial automation, for yield analysis, for data lake, for higher quality products. Very important in Industry 4.0, as it's often referred to, right? The next generation of smart manufacturing and smart design. So let's talk about EDA. If we'd had this conversation even just a few years ago, there would have been a tremendous amount of skepticism. What is cloud? How can it be secure? How can EDA ever move to cloud, right? Today, cloud for EDA is a reality. It's happening. We're at the beginnings of it. It's in production. We ourselves at Amazon, we use our own cloud, of course, for silicon design. We know it works. We know it works very well. And we have customers externally that use AWS for the same thing, for things like timing verification, right? Static timing analysis, regression testing, right? RTL, mixed signal simulations, many, many use cases. And not only in EDA, as the previous speaker from Univa described, but in other industries as well. Cloud is very real for enterprises that need high scale, high performance simulations, verifications, and other use cases. So let's drill a little bit deeper into what you need to run design and verification today. And this is true whether you're running in the cloud or you're running on-premise today. These are some of the factors for success in running design and verification. Again, either on-premise, in a co-located data center, or on the cloud. First and foremost, you need security, right? This is almost job one in a semiconductor company. to lock down the security of their IP, but perhaps more importantly, to lock down the security of foundry IP, of third-party IP that you're getting from your IP partners. Security is incredibly important. You need that. You need governance as part of that. Who's accessing the data, under what conditions, right? Of course you need performance. This is particularly true if you're operating software that you're paying license fees for. And those license fees may cost you dramatically more than the underlying IT infrastructure. So the more performance you can get out of your clusters, the less you'll pay for licenses. Or perhaps in a more friendly way to put that for the EDA vendors, for the same license spending, you can get more done, which may incent you to buy more licenses in the future because you're so happy, right? So CPU performance, very, very important. And the ability, as I'll describe in a moment, to optimize CPU performance for different applications, because different applications require different types of servers. Many applications today in EDA are becoming memory intensive. Static timing analysis, for example, DRC, these back-end verification runs increasingly require more and more RAM. They're just RAM hungry, right? But not every application is. So optimizing for RAM is very, very important. It's one of the major cost factors, as you probably know, in deploying an EDA cluster is the RAM. Networks are important. Now, networks are not so important for all applications in EDA. The biggest area where network performance helps you is in accessing shared file systems. So the higher performance a network you can deploy, the less of an issue storage bottlenecks will be. And for some applications that require node-to-node communication, that performance of the network can be very, very important to get high throughput. Storage as well. I mentioned a moment ago how important storage is. And if you operate EDA clusters today, you know that most of your tuning is going to be on the storage layer, right? It's on making sure that NFS is not bottlenecking your applications, that all of the applications have access to the files they need when they need them. That's a very, very important part of the EDA performance story. Another area is automation. And automation, if done right, can help you optimize all of these other factors, right? So whether you're using products such as LSF or SunGrid Engine, Univa Grid Engine, open source schedulers, customized workflow tools, that automation is very, very important. And in a hybrid scenario where part of your application is running on-premise or in your existing EDA clusters and part in the cloud, automation is very important as well for storage synchronization to make sure that you can run the jobs you need when you need them with the data that you need. So storage is important, automation is important, compute is important. In many applications, whether it's physical synthesis or board layout, for example, you also need remote graphics. You need a remote desktop that's 3D graphics enabled. So having access to graphical capabilities in the cloud or on-premise through remote desktop or through visualization software is equally important. And lastly, ISV support, the EDA vendor support. This has been an area that the EDA vendors have been increasingly progressive in. Cadence has announced this week their Cloud Passport, for example. Other EDA vendors, emulation capabilities in the cloud or via the cloud, the ability to migrate your own licenses to the cloud. It's becoming much easier to have that conversation with your EDA vendors and actually migrate to the cloud. That's changed dramatically in the last year. So EDA vendors have been very supportive of cloud deployment. That should not be an issue for you. But lastly, I mentioned this before, scale. Excuse me. Scale is so important for next generation applications in semiconductor design. If, for example, you are going to the most advanced nodes, and previously you had been at 14 nanometer, for example, now you're going to 7, suddenly the workloads change dramatically. Where previously, perhaps your RTL verifications, your regression tests had taken up most of your cluster, most of your compute resources, now suddenly it's the back-end verification, right? That problem becomes more and more difficult. And so your compute needs change, and your needs for scale can change dramatically, right? Getting close to tape out, you don't want to miss the schedule, you want to throw as many servers as the problem that you can, but you don't have the servers. And this is where cloud becomes increasingly important, to get access to those short bursts of high memory servers, to get those jobs done and turned around. Very, very important. We heard in the previous talk from Univa about a 1 million core run. And think about that statement. If you were here for the session previously, Univa described recently running a 1 million core single cluster job on AWS in a single region using 3 availability zones, 1 million cores, right? That's the scale that you can now think about. So think about this in the context of computer-aided engineering and electronic design automation, and there's many workloads, not just core EDA, but adjacent workloads, magnetic simulations, material simulations, structural simulations, right, to do next generation products. What could you do if you had 1 million cores tomorrow? And that's the kind of thinking that we can have now in EDA. This is not pie in the sky, as the term was used yesterday. This is not aspirational. This is real. You can do it. It requires automation. It requires some intelligence around software and storage optimization, but you can do it. And this is a very exciting area in some of these emerging workloads in semiconductor. Beyond EDA, lithography, for example, the ability to launch hundreds of thousands of cores, millions of cores when you need them for these big simulations will change the rules of the game for semiconductor design. Let's talk about architectures and best practices. If you think about a traditional EDA stack today, it looks something like this. This is kind of badly drawn because my PowerPoint skills are terrible. But the idea here is that whether you're doing EDA or you're doing structural simulations, engineering simulations of all sorts, we've really settled on a pattern of IT that's existed now for literally 2 decades, maybe longer. And that pattern is that you've got a cluster that's dedicated for engineering. It's probably shared between different teams. In the semiconductor world, you probably have one cluster there that's for all of your EDA jobs, whether it's front-end verification or it's back-end timing analysis, DRC. It's just one cluster. Or maybe it's multiple clusters of different generations. You have the need to manage software licenses, so you've got a license manager in there somewhere. Hopefully you've got more than one because that's a single point of failure. You're going to have a head node that runs a scheduler. That scheduler is going to be communicating with individual slots that are being deployed on physical servers in the data center using job scheduling software. If you're the IT team that's managing this cluster, your job is to keep that cluster fully utilized so that you can report good numbers to the COO to say, yes, I'm making good utilization of the hardware that we purchased and deployed over some period of time. If you're the engineering team that's using that cluster, you actually have different goals because you're measured on how fast can I get the design done, which might mean that you want to burst a lot of workloads right now, but you're constrained by IT. And so you put things in the job queue, they take forever to finish, regressions are delayed and so forth. So there's these 2 different motivations of the IT teams that are managing this and the users that are using it. But this pattern has existed for a while. It exists because it's powerful, it works well. It's often accompanied by high-performance shared file systems. Perhaps if you have multiple sites, you're using storage caching or synchronization to get the data from one to the other, right? It's a complex environment, but it's well understood in the industry. Most recently, there's a trend toward remote desktop, and so in this stack, you might have some servers for remote desktop, for a VDI, right? Virtual desktop. So that pattern is not particularly scalable, and it's not particularly scalable if, as I said earlier, your workloads are changing dramatically. Maybe you've got new projects that come in that you didn't expect. Maybe there's some merger or acquisition going on. Maybe you've divested in part of your business. Maybe you realize in going to 7 nanometer that your needs for verification on the back end are going to explode, and you didn't expect that, right? And suddenly this inflexible cluster becomes a boat anchor. In fact, if you were a fabless semiconductor company, you might be wondering why you're operating a data center at all, because if you're a fabless semiconductor company, your only staff should really be smart engineers who can do semiconductor design, lawyers to protect your IP, and marketing people to brand it, and you don't need anyone else. But instead, you've got large groups, organizations to manage that. Now I'm being a little facetious here. You always need, IT staff. You're always going to need security and governance to manage IP, but you don't actually need the physical data center. Because now what you can do is you can think about migrating to the cloud. Initially, this will be a hybrid environment. You'll have existing infrastructure in your existing EDA data centers, but you want to begin to migrate workloads intelligently to the cloud, right? The difference in the cloud, you can create an environment that looks and feels very much like the legacy data center. It can have license managers, it can have cluster head nodes, you can use existing schedulers just as you did before. The major difference is both the compute and the storage resources can scale up and down automatically in response to need. You don't need to predict 6 months in advance how many servers you're going to need for physical verification, for physical synthesis and DRC and static timing analysis or lithography or whatever else you're doing in the future. You can get these on demand through a variety of pricing and mechanisms and launching mechanisms on the cloud. You can get these on demand. In fact, in many of our customer cases, you don't even need to plan days in advance. You really could just monitor the job queue for how many jobs have been queue subbed into the environment and automatically spin up the servers when the job queue starts to grow, right? Automatically growing and shrinking the resource. And similarly on the storage side, rather than having a very large amount of expensive shared file systems sitting there all the time, you can actually grow and shrink your storage needs for that high performance storage as you need them, as you submit job decks and workflows to that cluster. Pulling data from lower cost object storage, right, more durable object storage, into local shared file systems, right, that are needed in the course of a run. And then you optimize. You start to create different scalable clusters for different applications. So maybe this is a cluster that's relatively low memory and high clock speed, and this is high memory, right? Different IT resources, different server types for different applications, optimizing your workflow as you go. And that optimization should never stop, because in the cloud providers, AWS included, are always innovating on new server types, right? So you never want to stop optimizing. You want to continue to look at the available resources in the cloud, look at your application needs, and optimize for the highest possible performance, highest throughput, EDA license savings, for example. In our case, and I've summarized here, we have instance types that are compute optimized. There's many more than I've shown here. We have storage optimized instance types. We have RAM optimized instance types. We even have accelerated instance types using FPGAs, for example. For some niche use cases in EDA, these could be quite powerful. And GPU use instance types as well. And these are continually being updated. The latest generation processors, the latest storage architectures, continuing to innovate. And the minute that we have something available in the cloud, it's available to you. You don't have to wait for a procurement cycle to get it. And then similarly on the storage side, I mentioned before that storage performance is very, very important for EDA. EDA applications are relatively old, they're legacy, they demand high-performance shared file systems, they do a lot of communication at the file layer, right? And this does require that you tune and create high-performance shared file systems that are well optimized for the specific applications. We can help you do that. We have white papers, we have best practice architectures. But to summarize, you have access in the cloud to different types of storage, ranging from on the right, object storage, which is really the lowest cost, highest durability, most reliable type of storage in the cloud, but it's object-based, it's not shared file, to the ability using block storage devices to handcraft or create through automation different types of storage architectures, whether it's a block storage device that's connected and rated and to a specific EC2 instance, or perhaps that creates a shared file system that can be used across your cluster. And that shared file system could be temporary or it could be persistent, really depends on your needs. We also have a managed shared file system service, Elastic File System. It's designed for durability, flexibility, automatic scalability, and has great performance for many types of applications found in EDA. But the point here is that there is no one storage architecture that's best for all applications found in EDA. It's very important to optimize for specific applications to get the highest possible performance, and we can help you with that. Our partners can help you with that. We have many learnings from our external customers as well as internally from our own semiconductor teams, how to optimize storage and compute for EDA workloads. So I want to summarize here. When we look at enterprise adoption of cloud across industries, not just in EDA and semiconductor, but in areas like pharmaceutical, financial services, energy sector, oil and gas, life sciences and healthcare, national security. The pattern is very clear, and what we see in these customers, large enterprises and relatively small organizations as well, is that they begin with a distinct problem that needs to be solved. Could be a proof of concept project in running static timing analysis, for example. It could be a data lake kind of a project where perhaps we're pulling manufacturing data from our various facilities and trying to create a data lake and deploy get some insights out of that data. Start with a compelling problem and solve that compelling problem using cloud. Innovate rapidly. Use a startup mentality for that first project. Use a DevOps mentality. Be agile. Once you've got a few of these under your belt, if you will, you've got some experience with cloud, then it's very important to build a proper foundation for migration. And what I mean by that is governance. What does your IT security really look like on-premise, and how can you improve that when you move to cloud? What's your cost governance model, right? How do you collaborate with third parties using cloud? Put the foundation in place after you've done some initial projects, because then you can begin a wholesale migration of large numbers of IT applications, core IT applications for the business, line of business applications, digital marketing applications, data lake applications, but more importantly, IP critical, security critical, business critical applications. They really do require that foundation be put in place first. And this is where existing IT teams, the support teams that operate data centers today, can really enhance their skills and become more important in the organization, because now they've got bigger levers, they have more scale to work with, and they have more capabilities for security and governance in the cloud than they had in the previous infrastructure. And I want to repeat that again. We've got numerous examples in CIOs and of organizations stating publicly, once they've gone through this and they've moved to cloud and understood security of the cloud and governance in the cloud, they've realized that in the cloud they can be far more secure than they were in their on-premise environments, because we have the scale, we've got the capabilities for encryption everywhere, for governance, for monitoring of activities that you didn't expect internally. The cloud is a very secure place to do design and verification and to do other critical applications for enterprises. But once that migration has become common and you've started to migrate, then exciting things happen. This is particularly true with data lake. If you're not familiar with that term, a data lake is the idea that using cloud, you can begin bringing data from all kinds of disparate sources. And in semiconductor, I'll just give you some examples. You've got data that comes out of your job queuing software. You've got job data, log files. You've got data that comes out of your IT teams, perhaps out of Splunk and other tools. You've got data that's perhaps coming from manufacturing facilities and test facilities, right? You've got data from your internal engineering resources and your job schedules and so forth, human resources data. You've got customer data. If you're working with a foundry, you perhaps have some data coming from the foundry. What does all of this data have to do with each other? You actually don't know. What's most important is you don't know what you don't know. If you bring all that data into a data lake in one place with good governance, now you can begin to apply data science to it without actually being a data scientist. You can start to deploy machine learning algorithms, you can start to deploy advanced analytics against it and begin to uncover insights, right? Design for manufacturability, EDA license utilization, right? Staff utilization, failure rates of products out in the field, yield analysis. Data lake is one of the most important places to start when you think about the first project and how you can reinvent the business later. And we've got many examples and case studies I'm happy to share if you're interested in how design and engineering organizations are using data lake in combination with EDA and HPC workloads to develop next generation, higher quality, higher yield products. We're seeing this in the front end design, we're seeing it also, the beginnings of it back in foundries as well. It's an exciting time for cloud adoption. Give you just a few examples of, two examples of customers that are taking this strategy, starting with specific needs, specific projects, and moving from there. We have a case study recently with NXP Semiconductor, for example. They actually started quietly back in 2012 to migrate some of their EDA workloads, and they haven't divulged publicly which ones, but their core EDA workloads all the way back to 2012, moving those to cloud. Now, they didn't have to tell the cloud provider. They may or may not have had the discussion at that time with the EDA vendor. You can simply extend your current data center environment to the cloud using VPN, extending your network, putting security in place. Many customers do this, right? Working with the EDA vendors, though, they've been able to optimize this, and working with us, of course, to optimize storage performance and compute. They're getting higher and higher performance, faster and faster throughput. And again, I want to emphasize again the need to continually re-optimize your workloads, and that was certainly the case with NXP Semiconductor over time. Another great example is Xilinx. Now, this is not core semiconductor EDA case study per se, but the Xilinx Vivado tools that are used for FPGA design, which are now available, by the way, on AWS for use with our FPGA instances, that requires a large amount of testing because the Vivado tool suite, the Xilinx tool suites, those are EDA tools. They're not used for chip design, they're used for FPGA development. But they have simulation, they have synthesis, they've got place and route, they've got many of the same technologies that you find in chip design. Xilinx has been migrating regression testing for Vivado, for their design tools, into AWS. And others are as well, actually. Cadence has talked publicly about their own experience in migrating EDA software regression testing to AWS, very successfully, right? So those learnings at Xilinx and Cadence and others are helping those vendors help customers with their own cloud migrations. So it's an exciting time. So that was a summary. There's much more that you can learn, and we're happy to have a deeper discussion. We have a booth right over there in the Design Infrastructure Alley, a big AWS logo on the blue screen back there, or reach out to me directly. I'm happy to connect you with solutions architects, with technical experts to go deeper on the topic. Thank you for being here today. I'm happy to answer a question or two while I'm here. Thank you. Are there any questions? I'm standing between everyone and beer. Yes, please.
When EDA software licenses, they typically say this is by the hour. You get to run an hour of Verilog. But where are the hours spent on a slice that has 20 CPUs or 100 CPUs, high memory or slow memory or fast memory or fast disks and slow disks, still cost me an hour, right? When are we going to have it be more related to how much work is done versus time?
Well, that's a great and controversial question. I'm glad you asked it. So yes, the traditional licensing model for EDA is that you're running per thread, right? You've licensed, and it's not typically per hour, it's licensed for an entire year. It's a subscription basis. And so to optimize license spending, you have to overcompensate in high performance, expensive IT. And so it's super important that when you migrate to cloud, that you optimize to get equivalent or better performance on a per thread basis in the cloud than you had on premise. And we can help with that, absolutely. You don't want to have lower performance or you're going to spend more in licenses. Your point is well taken though, and this is a conversation that you really should have with EDA vendors. Is there an alternate model in the future where you're actually monetizing, if you're the EDA vendor, the results delivered, not the artificial metric of how many threads are running and for how long? Because the nature of computing is changing. And it's not simply that you're going to run on the same kind of processor today and tomorrow. GPU acceleration, for example, really dramatically changes that equation, right? In some applications. Yeah, thank you.
What is the cost of uploading, downloading gigabytes or terabytes of data which may be necessary for debugging, for sign-off, for review from my premises to the cloud and back?
Yeah, it's a great question.
It can be very slow.
Yeah. Well, there is a cost, of course. You know, the cost of uploading is free for data, but actually to optimize your cost of migrating data back and forth, whether it's for interactive workloads like remote desktop or synchronizing data or doing a one-time push, there's many different options. For example, for the one-time push of uploading a large amount of data, maybe your initial regression suite after which you're just going to synchronize, there's a physical ingest capability. We call it Snowball, where you could put 100 terabytes into a box that will ship itself to an AWS data center, right, in a secure manner with your keys. That's one option. Another option that many of our enterprise customers, probably most of them do, is what's called direct connect, where you're not pushing data across the public internet using VPN and paying connection costs, but you contract with a direct connect provider to have dedicated links to the cloud. It's very common in areas like pharmaceutical, for example, and energy sector, and broader manufacturing, where you have a lot of data that you need to push back and forth to do big simulations to these runs. There's a lot of ways to optimize storage transfer costs. Yeah, thank you. Yeah. All right. Thank you so much, and enjoy the session today, and please enjoy the Design Infrastructure Alley and the happy hour later. Hi, how are you?